In this video we're going to look at how differential equations that we have studied in Unit 3 and 4 of your mathematics and also in Unit 4 of your further mathematics may be applied to some mechanics problems. In particular, in this video, to kinematics problems. To begin with, we need to set up one or two conventions, and the first one is to make sure that once we have said what the positive direction for our motion is, then that also gives us the positive direction for the velocity and also the positive direction for the acceleration. The second thing we need to realise is that there's two or three different ways of writing acceleration. We know that acceleration is the rate of change of velocity, so we've got a equals dv by dt. But v is the same thing as the rate of change of the displacement, so we've got v is dx by dt, so we can write a, which is dv by dt, is the same thing as the derivative of dx by dt. In other words, it's d2x dt squared. Another way of writing the acceleration is if we've got a equals dv by dt, then the chain rule tells me that dv by dt is the same thing as dv by dx times by dx by dt. But dx by dt, if x is the displacement, dx by dt is simply the velocity. So we've got dx by dt equals v. So in other words, we've got a, the acceleration, is the same thing as v times dv by dx. So we've got three different ways of writing acceleration. We can write it as dv by dt, we can write it as d2x dt squared, and we can write it as v dv by dx. And during the course of this module, you'll find that we're writing an acceleration in these three different ways quite frequently. The first one of the three types is useful when we're trying to find a relationship between velocity and time. The second is useful when we want a relationship between displacement and time. And the third of these forms for acceleration is useful when we want to find a relationship between velocity and displacement. Now, up to now, all of the kinematics examples that have been considering, the forces acting have been functions of time, and this has meant that an application of Newton's second law will give the acceleration of the particle, and then integration will give the velocity of the particle, and a further integration will give the displacement of the particle. However, frequently we'll find the forces acting are not simple functions of time, but may depend on either the velocity or the displacement of the particle. And in these cases, Newton's second law is going to lead us to a differential equation. And in the course of this unit, we're going to find several cases when this is the case. So, for our first example, we have a particle of mass 2 kilograms. It's travelling on a horizontal line against a resisting force of magnitude 8 plus 5v newtons, where v meters per second is the speed of the particle. If the particle has an initial velocity of 20 meters per second, we've got to write down a differential equation linking v and t, and hence find the time taken for the particle to come to rest. As with the vast majority of mechanics problems, we should certainly start this question off with a simple diagram. So there's my particle, and we're defining the positive direction to be out to the right on our diagram. So that means that's also the positive direction for the velocity. and also the positive direction for the acceleration. Now in this case we're asked to write down a differential equation linking v and t. So we will use a equals dv by dt as our form for the acceleration. We've got the resisting force, which is opposing the motion, has magnitude 8 plus 5v. So if we apply Newton's second law to the right, simply because of the direction, that's our positive direction for the motion, the resultant force is minus p, must equal the mass times the acceleration is 2 times a. So we've got minus 8 plus 5v equals 2 times dv by dt. And this equation we can solve by a variety of methods that you've probably already met. In your mathematics units, you'll have met the method of separating the variables, which is certainly one way of solving this equation. Alternatively, the equation could be solved by using an integrating factor, which is a method that you'll have met in Unit 4 of the Further Mathematics. For this example, we're going to continue by using the method of separating the variables. So, we have if we've got the differential equation was minus 8 plus 5v equals 2 dv by dt. So getting all the v's on one side, we've got minus 1 equals 2 divided by 8 plus 5v times dv by dt. Integrating each side with respect to t, we obtain the integral of minus 1 is equal to the integral of 2 over 8 plus 5v times by dv by dt. But integration by substitution says that our dv by dt part of this integral can be replaced simply by dv. So we've got the integral of minus 1 with respect to time is equal to the integral of 2 over 8 plus 5v integrated with respect to v. Minus 1 will integrate to minus t plus c, and our 2 over 8 plus 5v integrated with respect to v becomes 2/5 of the logarithm of 8 plus 5v. Now, we haven't used the initial conditions yet. We were told that initially the particle had a velocity of 20 meters per second, so when t equals 0 we've got v equals 20. So that tells me that 0 plus c must be 2/5 of the logarithm of 108. In other words, c is 2/5 of the logarithm of 108. So we've got minus t plus 2/5 of the logarithm of 108 equals 2/5 of the logarithm of 8 plus 5v. In other words, we've got t is 2/5 of the logarithm of 108. Take away 2/5 of the logarithm of 8 plus 5v. So when v equals 0, so that's when the particle comes to rest, we've got 2/5 log of 108 minus 2/5 log 8 must equal t. In other words, t is 2/5 of the logarithm of 108 take away the logarithm of 8. And when we're subtracting logarithms, that's the same thing as just dividing the numbers themselves. So logarithm of 108 take away the logarithm of 8 is the same thing as the logarithm of 108 over 8, which cancels down to 27 over 2. So we've got the time for it to come to rest is when t equals 2/5 natural logarithm of 27 divided by 2. Part B of the question, we've got to write down a differential equation linking v and x and find the displacement of the particle from its initial position when it comes to rest. So, again back to our diagram. Now this time we want a differential equation linking v and x. So for the acceleration we're going to use the v dv by dx format. And again we've got the resisting force of 8 plus 5v. So when we apply Newton's second law, we've now got minus p equals 2a, exactly as before, but this time that's minus 8 plus 5v equals 2v dv by dx. And again, this equation can be solved by separating the variables. So our equation we've got is minus 8 plus 5v equals 2v dv by dx. Dividing each side by 8 plus 5v will get all of these on the one side for me. So I've got minus 1 is 2v over 8 plus 5v dv by dx. So integrate each side with respect to x, and then realizing that the dv by dx part of it can be replaced by simply an integration with respect to v. Then we've got to think about the integral of 2v over 8 plus 5v. Now 2v over 8 plus 5v can be written using polynomial division as 2/5 take away 16 over 5 times by 1 over 8 plus 5v. So check you can do that polynomial division and it comes out to something like that. So we've now got the integral of minus 1 with respect to x is the same thing as the integral with respect to v of 2/5 minus 16 over 5 times by 1 over 8 plus 5v. The left hand side is minus x plus c. The right hand side is going to be 2/5 v minus 16/25 times the logarithm of 8 plus 5v. We've got to find out what c is at this stage. Now we know that when x equals 0, v is 20. So that gives me 0 plus c equals 8 minus 16/25 of the logarithm of 108. So that tells me that c is 8 minus 16/25 of the logarithm of 108. So we've got minus x plus 8 minus 16/25 logarithm of 108 equals 2/5 v minus 16/25 logarithm of 8 plus 5v. When v equals 0, that's going to give me minus x plus 8 minus 16/25 logarithm of 108 equals 0 minus 16/25 logarithm of 8. So, if we make x the subject of that, we're going to end up with x equals 8 minus 16/25 log of 108 plus 16/25 logarithm of 8, which we can rewrite as 8 minus 16/25 of the logarithm of 108 over 8. Now let's move on to our second example. So we have a particle of mass 5 kilograms, travels on a horizontal line against a resisting force of magnitude 30 v to the 1.5 newtons, where v is the velocity of the particle. The particle has an initial velocity of 60 meters per second. Find the distance travelled before the particle comes to rest, and the speed of the particle when it has travelled halfway to its final position. Okay, so as before, we need to start off with a diagram. So when the displacement of the particle is x meters, then the velocity is v, and because we want an expression linking the distance travelled and the velocity, and we're not interested in time at all in this question, we're going to use the v dv by dx format for the acceleration. And the force that we've got acting is a resisting force of magnitude 30 v to the 1.5 newtons. Applying Newton's second law to the right, we've got minus p equals the mass 5 times the acceleration, which in this case becomes minus 30 times v to the 1.5 equals 5v dv by dx, which simplifies to minus 6 v to the 0.5 equals dv by dx. Now this equation we can solve by separating the variables again. So if we divide each side by v to the 0.5, we've got minus 6 equals v to the minus 0.5 times by dv by dx. Integrate each side with respect to x, gives me minus 6 integrated with respect to x is the integral with respect to x of v to the minus 0.5 times by dv by dx, which can be written as the integral of v to the minus 0.5 dv. Doing the integrations, we've got minus 6x plus c must equal 2 lots of v to the 0.5. Making use of the fact that we know that when x equals 0, v is 60, we get 0 plus c equals 2 root 60. So we know that c is 2 root 60. In other words, we've got 2 root 60 minus 6x equals 2 root v. Or alternatively, root v is root 60 take away 3x. It comes to rest when v equals 0, and if v equals 0, we've got root 60 minus 3x equals 0, which gives me that x is root 60 divided by 3. So the distance it travels before the particle comes to rest is root 60 over 3 meters. We also want to calculate what the speed is when it's gone half of the distance. So the particle comes to rest after travelling 1/3 root 60 meters. When it's halfway there, that's going to be when x is 1/6 of root 60, in which case root v is root 60 minus 3 times 1/6 of root 60, which is 1/2 root 60, in which case v is equal to 1/4 of 60, which is 15 meters per second, when it reaches the halfway point. For our final example, we have a particle of mass 3 kilograms is constrained to move along the x-axis. Initially the particle is at rest at the origin. When a force P is applied to the particle, this force acts in the positive x direction, and t seconds after the start of the motion, this force has magnitude 30 e to the minus t newtons. When the particle has a displacement of x meters and is moving with velocity v meters per second, its motion is opposed by two forces, one of 12 V newtons and another of magnitude 15x newtons. We've got to write down and solve a differential equation that links x and t. So we'll start off by having a diagram. So there's our starting point for the diagram. We're, in this case, wanting an equation linking x and t, so we're going to be using the velocity being dx by dt and the acceleration being d2x dt squared. Putting the forces onto the diagram, we have the force P, which is of magnitude 30 e to the minus t. And then we have the resisting forces, one of magnitude 12 V newtons and another one of magnitude 15x newtons. So if we apply Newton's second law to the right, we've got the resultant force, which is P minus Q minus R, must equal the mass, which is 3, times the acceleration. So we have 30e to the minus t minus 12v minus 15x must equal 3 times d2x dt squared. Or 30e to the minus t minus 12 dx by dt minus 15x equals 3 d2x dt squared. If we take all the x terms onto the right hand side and also divide through by 3, we obtain 10e to the minus t equals d2x dt squared plus 4 dx by dt plus 5x. So, the initial conditions for this differential equation, when t equals 0, we know the particle is at x equals 0 and that it's at rest, so dx by dt is also 0. So we've got the differential equation d2x dt squared plus 4 dx by dt plus 5x equals 10e to the minus t. And this is a second order differential equation, which if you've done the differential equation work in Unit 4 of the Further Maths, you'll know how to solve. So we start off by finding the complementary solution, which is the solution to the equation d2x dt squared plus 4 dx by dt plus 5x equals 0. That has auxiliary equation m squared plus 4m plus 5 equals 0, which has roots m equals minus 2 plus or minus I, which means that the complementary solution is of the form x equals e to the minus 2t times a cos t plus b sin t. The particular solution, well, we may as well try something of the form x equals alpha e to the minus t, in which case dx by dt is minus alpha e to the minus t, and d2x dt squared is alpha e to the minus t. So d2x dt squared plus 4 dx by dt plus 5x is going to be alpha e to the minus t, take away 4 alpha e to the minus t, plus 5 alpha e to the minus t, which is 2 alpha e to the minus t, which will equal 10e to the minus t if we have alpha equals 5. So we've got a particular solution is x equals 5e to the minus t. This means that the general solution of the differential equation is given by the particular solution plus the complementary solution. So we've got x equals 5e to the minus t, that's the particular solution, plus e to the minus 2t times a cos t plus b sin t, which is the complementary solution. Differentiating the expression for x gives me dx by dt equals minus 5e to the minus t. Take away 2e to the minus 2t times a cos t plus b sin t. Add e to the minus 2t times by minus a sin t plus b cos t. And we can now look at the initial conditions to find out the values of a and b. So we know that we've got initial conditions that when t equals 0, x equals 0, and dx by dt is 0. So, first of all, t equals 0, x equals 0 gives me 0 equals 5 plus a. So a must be equal to minus 5. And then dx by dt equals 0 is going to give me 0 is minus 5, take away 2a plus b. And that forces me into having b is minus 5. So we've now got our solution, which is x equals 5e to the minus t minus 5e to the minus 2t cos t minus 5e to the minus 2t sin t. And now we want to use the solution and a graphical calculator or graphing software to describe the motion of the particle. So the displacement time graph suggests that the particle starts moving in the x direction, reaches a maximum distance of roughly 0.9 meters from the starting position, and then as t tends to infinity, the particle is getting closer and closer to its starting point.